Hello, everyone, and welcome back. We are finishing up with the MCT4C course. This is the Math for College Technologies, grade 12 course. We are on Unit 4. This is the review of lessons 16 to 20. So this is the end of the course for us. And so what topics are we going to be reviewing? Well, we're going to be having a look at the scalar multiplication of vectors, conversions involving metric and imperial units, areas of shapes. This will include area of 2D shapes and surface area for some 3D shapes. Though note that the review on this will be much shorter just because in the lessons themselves, we go through an example of each of them. And so if you've done an example of each of them, we'll limit our uh, we'll limit our examples to a couple composites, some circle properties, as well as arcs, sectors, and segments of a circle. And so what we have for today is the Desmos scientific calculator. We'll need that for everything after the first couple of points. Okay, so here, example one, scalar multiplication of vectors. So we have triangle, rectangle ABCD. E is the midpoint between A and B. AE is equal to vector U, and UAD is equal to vector V. And we need to express each vector in terms of U and or V. Okay, so here, how do I make vector AB? Well, you can see vector AB is composed of two vector U's. So here we can claim that vector AB is equal to two vector U's. How about vector AC? So that goes from the bottom left corner to the top right corner of this. Well, we can see that we're going to need a vector V as well as those two vector U's. So vector AC will be equal to two vector U's plus a vector V. Okay, what about vector CE? Okay, so we start at point C and we go down. So you can see here that we need a negative vector V because we need a vector CB and its equal vector would be dA, so that'd be negative V. And then we need the opposite vector of AE, which will be EA, which will be a negative vector U. So vector CE will be equal to negative vector U minus sign vector V. Or if you want, you could write this as negative vector U plus sign negative vector V if you so choose. Lastly, but not leastly, what about a vector dB? So dB goes from the top left to the bottom right corner. And so here, you can see that we're going to have two of those vector U's because we're moving from the left to the right. And we are going downwards. So we need a negative vector U to go downwards. So that'll be 2U minus vector V. Okay, so number two, sorry. Draw each of the following based on the given vector diagram. So here we have we have a vector V and a vector U. And for the first one here, they want us to draw three vector U's. Okay, pretty straightforward. All we need to do is to have three vector U's lined up head to tail. So this will be one vector U, two vector U's, and three vector U's. So we can label this as such. And we claim that this is going to be three vector U's. And the other one we need is a negative vector U followed by negative three vector V's. So that means we need the opposite. We'll start off with the opposite of vector U. So we'll draw a horizontal arrow, draw the arrow on the other side. So this is a negative vector U. And then we need three vector V's. So that's instead of going towards the northwest, we're going to go towards the southeast instead. So that'll be 1, 2, 3. So that'll be three negative vector V's. Okay. And the resultant here will be from the tail of vector u to the head of negative 3v will be negative u minus 3 times vector v. There it is. Okay, so like I said, quick little review of those subtopics. Uh, example 2 has us deal with converting metric units. And so we're going to have our no need chart. And we have, again, from the textbook, the metric and imperial system chart. So we just copy and pasted that. Keep in mind, the textbook uses these values. So if you don't use these values specifically, your answers will differ from what the answers in the book are going to be. Okay, because they just assume this is what you're going to use. Okay, so for this first one here, we want to convert 12 feet to inches. And so we know that 12 inches is equal to 1 foot. So it doesn't matter how you fill this no part out. So we can say 12 inches is 1 foot. What's important is that you fill out the other side in the corresponding manner. So we need 12 feet, but we want to know how many inches that's going to be. And so from here, we set up our corresponding ratio, namely 12 over 1 is equal to x over 12. Okay, we know we did this right because we could see inches to inches, feet to feet. We'll use the method of the means and the extremes. So we're going to take 12 times 12 and set that equal to 1 times x. 12 times 12 is 144. So x will be equal to 144 inches. Okay, what about 50 kilometers to miles? So again, having a look at our chart, we can see 1 mile is approximately 1.609 kilometers. And so we know that 1 mile is equal to 1.609 kilometers. And we're curious as to how many miles there are in 50 kilometers. And so writing down our ratio, we can see that 1 over 1.609 will be equal to x over 50. Using the method of the means and the extremes, we take 50 multiplied by 1 as being equal to 1.609 multiplied by x. And so x will be equal to whatever 50 multiplied by 1 divided by 1.609 is. And so using the Desmos scientific calculator, as that's the only calculator we need today, we take 50 multiplied by 1 and divide it by 1.609. And we'll take 2 decimal places, and we can see that the solution to this will be equal to 31.08 miles. This makes sense because a mile is longer than a kilometer, so you'd expect the answer for this to be smaller than 50. So there you go. Okay, so here, which is larger, 30 square feet or 3 square meters? And then we need to prove our answer. The prove our answer part is irrelevant for this since we don't have a way to directly convert between feet and meters yet. So we'll need to work on that. So let's have a look at our measurements here. We need to end up in feet or meters somehow. And so if you notice here that 1 foot, let's work in green, I guess. Let's try this one more time. There you go. 1 foot is equal to 30.48 centimeters, and there are 100 centimeters in a meter. So this seems like the best way to convert is we're going to convert both of these to centimeters and compare it that way. So here we will convert both to centimeters. Okay. So with respect to feet, recall 1 foot is equal to, and we can see from above, that's going to be 30.48 centimeters. And so we know that 1 foot square will be equal to 30.48 times 30.48. Because remember, when you convert areas, you need the conversion twice. So if I take 30.48 and times it by itself, I end up getting this 929.03 centimeters squared. Okay. And so if I know that 1 foot square is equal to, or a square foot is equal to 929.03 centimeters squared, then I'm curious as to how many centimeters are involved in 30 square feet. So solving this ratio, we have 1 over 929 is equal to 30 over x. Using the method of the means and the extremes, we end up with 1 times x is equal to 30 times 929.03. So x will be equal to, so we take 30, multiply it by 929.03, and we get some large number. In this case, we get 27,870.9. And these are going to be centimeters squared. We'll work in black now. For meters squared here, it's worth noting that 1 meter is equal to 100 centimeters. And so 1 square meter will equal 100 times 100, which equals 10,000 centimeters squared. So you can see already the conversions between the metric system, much more reasonable to do, but that's okay. And so we know that 1 meter square is equal to 10,000 centimeters squared. And we're curious as to how many square centimeters there are in 3 meters squared. So the corresponding ratio will run as 1 over 10,000. And this is equal to 3 over x. Using the method of the means and the extremes, we have 1 times x is just going to be x is equal to 10,000 multiplied by 3, which is 30,000 square centimeters. And so now we can compare our two answers, and we can see 30,000 square centimeters is larger than 27,000. So that means that which is larger, 3 square meters is larger than 30 square feet. Convert both to centimeters or centimeters squared. Okay, so that's how we can prove that kind of response. All we did was convert them both to a common base and go from there. And if we were converting volumes, say this was 30 feet cubed and 3 meters cubed, then for 1 foot cubed, it would be 30.48 times 30.48 times 30.48. And the corresponding meter cube conversion would be 100 times 100 times 100, and so forth. Okay. Example 3, we have areas of shapes. So we have a cylindrical wheel of cheese. So think about maybe perhaps a larger brie cheese is cut into 8 congruent, meaning equal pieces. What is the least amount of wrapping required for each wedge of cheese? So we're assuming that these people can perfectly wrap this with no overlap. Okay. So recall the surface area, or the surface area of a cylinder, is equal to 2 pi r squared plus 2 pi rh, where pi is equal to 3.14. Now, what do we need to do here? So that's what we need in order to get started. So here we're talking about this cylinder piece of cheese here. So keep in mind, we can take out this cylinder, right? So here we're going to have the side, the top, the side, as well as the bottom. But when we take out one of these cylinders, oh, we almost got there. Go. We're also going to need the two sides of the wall. So we're going to need this part of the wall as well as the back. And so here we need the surface area of a cylinder formula to get us the outer wrapping of the cheese. But then we also need two walls for the inside of the cheese itself. Because remember, when you take out the slice of cheese, we're assuming that that part's going to be wrapped as well, right? Because otherwise, it would just, why would we cut it into pieces? And so here we need the surface area of a cylinder, but then we need to divide that by 8. Since we are using the top, the bottom, and the lateral surface area, we just need an eighth of it though. And then we need to account for the two walls afterwards. So keep in mind, for the wall of the cheese, we know that this height is going to be 10 and that the length of this is going to be half the radius. So it'll be 15 because it'll be 30 divided by 2. Okay, so those will be our two surface areas to worry about. And let's compute this. So for the surface area of the cylinder, this will be equal to, now it's worth noting that for us, R is going to be equal to half of 30, so it'll be 15, and H will be equal to 10. So the surface area will be 2 times 3.14 times the radius 15 to the power of 2 plus sine 2 times 3.14 times 15 times 10. But then we need to take this entire answer and divide it by 8 afterwards because we only want 1/8 of this. So this will be equal to what? Well, we type this in. So this will be 2 times, and again, you could type this in as you see it, 3.14 times 15 squared plus sine 2 times 3.14 times 15 times 10. And then afterwards, you can see that the surface area of the whole thing is 2355. So why don't we write that? So this will be 2,355 divided by 8, which means that the outside portion of that slice of cheese will be 294.38 after rounding, and these are in centimeters squared. So this is a big piece of cheese. But now we need these inner walls, right? And there's two of them. So the area of the walls will be length times width. And so that there's going to be two of them then. So we times that by 2. So this will be 15 times 10. Afterwards, we times this by 2. So on our calculator here, 15 times 10 times 2, that's going to give us 300. So this area will be equal to 300 centimeters squared. And you can see we actually need more for the walls than we need for the outer wrapping of the cheese. So there you go. And so this total will be equal to 300 plus 294.38, which gives us a total of 594.38 centimeters squared worth of wrapping required for this cheese. And again, the basis for how this worked was that we had to find that the surface area of the entire wheel of cheese but we only want an eighth of it, and then we needed the two walls that would make up the inside of the cheese slice. Okay. Example 2, we want to determine the area of the following. So we've got a composite shape here. So we have three areas altogether. We have a triangle, a rectangle, as well as a half circle. And so we know our last option will be the area of the total will be the area of the first shape plus the area of the second shape plus the area of the third shape, A1, A2, and A3 respectively. And so let's figure out the area of the first shape is a triangle. So A1 is a triangle. So it has as a formula base times height divided by 2. So in this case here, we have a base equal to 2, and we have a height equal to 4. And so this area will be equal to 2 times 4 divided by 2. And on our calculator, if you just take 2 times 4 divided by 2, you'll get 4. And so this will be 4 miles squared. The second shape, A2, perhaps we can write the number 2 a bit neater. A2 is a rectangle. So the formula for the area of a rectangle, again, if you're ever not sure, just pull out the formula sheet or the notes from last time to help you. Not just on this one, but on all of them. It's just length times width. So here we have a length of 6 and a width of 4. So the area of the second shape will be 6 times 4. And 6 times 4 is just going to be 24 miles squared. Okay, so A2 is going to be 24. A1 is going to be 4. Okay, and I like just having like this extra side work off to the side so I can neatly talk about all of the questions. The last one is the half circle, right? So for the area of a half circle, that formula is going to be pi r squared, and then we just divide it by 2 because it's half of a circle. The only thing we need here is the radius. So the radius will be equal to 4 divided by 2. So it'll be 2. Because remember, we were given the diameter on this side, which is going to be 4, but we only need half of it. Consequently, half of 4 happens to be 2. Dotted lines on this are tough. I'll try my best. Okay. And again, we make the stipulation pi is 3.14. So the area of the third shape will be equal to 3.14 multiplied by 2 to the power of 2, and then we just divide this by 2 afterwards. So the area of this third shape will be equal to what? Well, so we take 3.14 multiplied by 2 to the power of 2, and then afterwards we divide our answer by 2. So A3 will be equal to 6.28, and this will be miles squared. So we'll put our 6.28 down here. And so consequently, the area of this total figure will be the sum of each of those three individual areas all added together. And on a calculator, if we do this, we take 4 plus 24 plus 6.28. And so the area of this thing is going to be 34.28 miles squared. And if you ever find yourself doing a home improvement project as well, you can often break down the more complicated shapes into simpler shapes. And even if it's not quite perfect, it'll be pretty close, especially if you have some sort of home garden project. You can break it down into a series of triangles and rectangles, and the amount of material that you need will be actually surprisingly pretty close. Okay, so that was surface area and two-dimensional area, and we only focused on 2 examples, or else we would be here for the rest of our time. But we do have to keep going. Example 4, we saw this earlier when we talked about matching properties of circles. And so I thought it'd be just a good review to review these questions because in lesson number 19, essentially you're just identifying parts of a circle to be able to make sure you understand what these are. And so to make this a bit easier, we do have Roman numerals here, but they're not going to fit over here. So I'm just going to relabel these 1, 2, 3, 4, 5, 6, 7, 8, just so that it fits a bit neater. Okay. And so we have 8 terms: chord, arc, central angle, secant, tangent, sector, inscribed angle, and segment. My recommendation for when you do these, do all the ones you know how to do for sure first, and then just kind of narrow it down. So for example, when I see number 7 here, I can see that we have a shaded area of the segment for AB. So immediately I know that the segment is going to be 7. Okay. So let's work in red now. So we take care of that one. And so just do all the ones you know how to do first. Additionally, when I look at number 5, we know that we studied in the last lesson, those are sectors. We found the areas of those. So we can go ahead and write that one down. The next one that kind of stands out to me would actually be number 8. This is what we call a tangent. A tangent is a line that passes through at only one point on, say, not just a circle, but on anything. They could also have a function that might touch at only one point here. So this is what we call a tangent. Similar to a tangent is what we call a secant, number 3. A secant just passes through 2 points and it's a line, hence why we have the little arrow on it. It can be confused with number 2, which is the chord. A chord is just a line segment between A and B, or just any 2 points on the line. And that leaves these leftover ones. The term we didn't study in this course whatsoever, apart from identifying it, was number 6. This is called the inscribed angle. So if you have an angle opposite 2 points A and B, that's what we call the inscribed angle. And now we have left over were the arc and the central angle. I left these till last because they actually are the most difficult to determine. And so if you have a look at number 4 here, we have an arc. This is a minor arc that contains A, C, and B because it's under half. And so here, number 4 would be the arc. And actually, as it turns out, number 1 is the central angle. And so this is just describing the angle that's formed between 2 points on the outside of the circle AB with the angle between them. So like I said, do all the ones that you know how to do, that you know for sure first, and it kind of makes it easier. If you try to go in order for this, like I think number 1 is actually probably the hardest one to figure out. That is the central angle. I think some people might put this as the arc or the sector, and then you might make mistakes. But you start with the really easy ones, such as the segment and the circle, sector. Then I moved on to the inscribed angle, secant, tangent, and was able to work my way down. Okay. Again, this is another support question from lesson 19. In the diagram shown right, O is the center of the circle, and it wants to know what the names of these various things are going to be called. And so what will we call OB? So from the center of the circle to the outside, OB would be called the radius. What would BC be called? So if we connect B and C together, we can also look from above to see what that was. That's going to be called a chord. CO is the same thing as OC. That's just O radius, right? What about BD? So so BD appears to be 2 radiuses, also known as the diameter. C, B, and to D, like so. We start at C, B, and we'll go all the way around. This is called an arc. This one is called the major arc. Okay, because it includes more than half the circle as well as the points we're interested in. What is angle BOC called? So it wants to know what's this angle in here. This is the central angle. Letter G, sorry. What kind of triangle is OBC? Well, what do we know about OBC? Well, there's O. So the OB and OC, these are both radiuses. And if they're both radiuses, that means they both have the same length. So that means this is going to be an isosceles triangle, because the definition of an isosceles triangle is that two of the sides are the same. Now, if we didn't know exactly, there's a chance that OBC could be equilateral, but I think that we can trust that the picture is trying to go out of its way to conclude for us that it's definitely most likely an isosceles triangle. And if we know that angle B is equal to 70, what is angle BOC? And again, I'll just draw this one down for us here. So here's our triangle, and let's label these O, B, C. So it's saying that if angle OBC is 70 degrees, what's angle BOC? So it wants to know this theta. Okay. Now, it's going to draw this out a bit bigger here because I ran out of space, which is quite common. Okay. So here, what do we know about BOC? Well, before that, if we know that angle OBC is 70 degrees, then that means angle OCB will also be 70 degrees. So it's worth noting that angle OBC is equal to angle OCB insofar as they are both 70 degrees. Now we know that the interior angles of a triangle are equal to 180 degrees. And so consequently, angle BOC will be equal to 180 degrees minus 70, which will be 40 degrees. And again, we take 180 minus 70, you do get that 40 degrees as an answer. Okay. All right, well, let's continue on. In the last lesson of the unit, we had to look at lengths, the arc length, area of a circle, and the area of a segment. And we wanted specifically what they were. And so for us here, what I've done is I just asked us to do one example of each. So consider a circle with radius 5 and a central angle of 60 degrees. Determine the arc length, area of the sector, and the area of the segment. Okay, so here, first thing we want to do is write down the formula for the arc length. So here we know that the arc length is equal to theta divided by 360 degrees multiplied by 2 pi r. And it's worth noting that we assume pi is equal to 3.14, like before. The radius will be equal to 5, and the theta, the angle of the central angle, will be 60. So this arc length will be equal to 60 divided by 360 degrees multiplied by in brackets 2 times 3.14 times the radius, which will be 5. And for these answers, we're going to take 2 decimal places. So this arc length will be equal to, so on the decimal scientific calculator, we take 60 divided by 360 multiplied by 2 times 3.14 times 5. And we do this, this particular arc length will be equal to 5.23 centimeters. So in this case here, this length arc will be 5.23 centimeters. Okay, what about the area of a sector? Well, the area of a sector is capital A is equal to theta divided by 360 degrees multiplied by pi r squared. And again, it's worth noting that r is still equal to 5, and the central angle is equal to 60 degrees. And so this area will be equal to 60 divided by 360 multiplied by 3.14. Instead of the radius, we write 5 to the power of 2. So this area will be equal to. So on the Desmos calculator, we could type this in as 60 divided by 360 multiplied by 3.14 times 5 to the power of 2. So this area is going to be 13.08 centimeters squared. Because remember, the areas are going to be units squared and the lengths are going to be just normal units. Okay, what about the area of the segment? Oh, I guess I should color this in. For us, this, oh wow, that turned out really well. This red portion is going to be the area of the segment. Sorry, the area of the sector. The area of the segment, and I fear I'm going to ruin my diagram, but we're committed to this now, will be this shaded in green portion there. So it appears to be quite small. So let's see if that's the case. So the formula for an area of a segment is listed above. Namely, it's A is equal to 1/2 r squared outside of pi divided by 180 times theta minus sine of theta. And again, we make the stipulations that r is equal to 5, theta is equal to 60, and for just because pi is 3.14. Okay, so this area will be equal to 1 over 2. The radius is going to be 5 to the power of 2, bracket pi, which is going to be 3.14 divided by 180 multiplied by the central angle, 60, minus sine of the central angle, 60. And again, you only get 1 mark for simplifying down the calculation. You get more marks for coming up with the calculation to type down. And so I do encourage you to practice typing these in carefully because it is easy to make a mistake. So find a method that works best for you with respect to typing these in. I just prefer to use the Desmos calculator and just type this all in at once. So this will be 1 over 2 multiplied by 5 squared multiplied by fraction button 3.14 times 180 multiplied by 60 minus the sine of 60 degrees. So this area is going to be equal to 2.26 centimeters squared. And if you kind of line up the diagrams, I guess that seems about right. Like if you're trying to eyeball to see if it makes sense, 2.26 looks believable. So I would be inclined to believe that's the case. All right. And so with that, we are complete. We're all complete the course. That's it. So at the end of this video, we've now covered pretty much the entire, covered the entire course. This combined with the notes in the learning materials will help you complete all of the key questions. However, should you have any questions, do feel free to reach out to us. We'll be able to get back to you and help you as best as we can. But for now, I wish you the best of luck on the next stage of your course or of life. Best of luck and goodbye for now.